All right, so here we are, section 2. So we're defining a one-to-one correspondence as a function that's one-to-one and onto. Okay, so it's called a one-to-one correspondence. All right, so now we're going to talk about something called cardinality, another definition. So two sets, A and B, have the same cardinality. So we say this is kind of a way of saying size. If there's a one-to-one correspondence from A to B. Okay, so it's got to be one-to-one and onto. Okay, so we're going to be talking about finite sets and infinite sets. So what's a finite set? A set that I can count, right? So like the null set, I can count the number of things in there. There's 0. And another finite set would be, something 1, 2, 3, right? Has 3 elements in it, right? So if I can count it with the natural numbers, 1, 2, 3, 4, 5, up to n, right? Then I call it finite. Okay, if I'm talking one finite set to another of the same size, it's one-to-one if and only if it's onto, right? So if I have a set of 3 and a set of 3, it can have a one-to-one correspondence if it's one-to-one and onto at the same time. Okay. Ooh, not true for infinite sets. What? An infinite set can have the same cardinality as a proper subset of itself. Okay, so let's talk about integers and even integers. So if this is the set of all integers, this would be the set of the even integers, right? So if all of this was the integers, the even integers would just be half of it, right? Okay, so let's see what we're going to do. So I'm going to start by drawing. So here I have negative, let me just make some dots here. So -2, -1, 0, 1, 2, right? So it keeps going this way and it keeps going this way because that's the integers, right? Okay. So now I'm going to draw the even integers, right? So the even integers would be like -2, 0, 2, 4, right? And they keep going this way and they keep going this way. Okay, so I am going to create a function. I have to create the function that is both one-to-one and onto. Okay, so my function is going to be f of n equal to n. So that's going to take an integer in here, right? And so let me just put the f is going to go from integers to even integers, right? So you're going to have to create these, so you have to know how to write this, right? So little f with the colon, this is domain, this is codomain, and this is what the function does, right? Okay, so now let's go show that it is one-to-one. So what does it mean to be one-to-one? That if I have f of n1 equaling n2, that I'll end up getting algebraically that n1 equals n2. So using the function, I get, look at that, it is one-to-one. Check. Okay, so now what does it mean to show onto? So what you have to state, I'm going to do, this is what I'm going to do. So for every y in the even integers, there is an n in the integers such that f of n equals y, right? So for every y I pick in here, in the even integers, there's going to be something that goes to it. And so this is where you do the scratch work, right? And so you say, okay, the y is equal to 2n, solve for the n, so I get y over 2 is n. So I say pick y over 2 for the n. So here we go. F of n is f of y over 2 is, okay, so now I'm using the function, right? 2 times y over 2 is y. Check, I got there. What? So what I just did is I showed that there's a 1-to-1 and onto function. So 1 goes to 2, 2 goes to 4, 0 goes to 0. So I've got a 1-to-1 and onto function from the integers to the even integers. So they have the same cardinality. So we're getting used to this kind of language.